we shall discuss absorption by organic molecule. UV absorption spectroscopy can be used for the quantitative determination of compounds which absorb UV radiation. In UV visible spectroscopy, organic molecules absorb UV visible light because their electrons, primarily in functional groups called chromophores, can be excited to higher energy levels. This absorption is particularly noticeable when molecules contain conjugated pi systems like double bonds, triple bonds, and aromatic rings. An electron is excited from a full orbital into an empty anti-bonding orbital. Each jump takes place energy from the light, and a big jump obviously needs more energy than a small one. Each wavelength of light has a particular energy associated with it. If that particular amount of energy is just right for making one of these energy jumps, then that wavelength will be absorbed. Its energy will have been used in promoting an electron. UV spectroscopy is useful in the structure elucidation of organic compounds. The presence or absence of a particular absorption band at a particular wavelength may be regarded as an evidence for the presence or absence of a particular chromophore in the compound. UV spectroscopy organic molecules absorb ultraviolet and visible light, leading to electronic transitions. They primarily undergo the process known as excitation of bound electrons. This occurs because UV light has enough energy to promote electrons from a low energy state, that is ground state, to a higher energy state, that is excited state. These electrons are found in functional groups such as double bonds, triple bonds, and aromatic rings. These transitions like sigma to sigma star, pi to pi star, and n to pi star occur at different wavelengths, providing information about the molecule's structure. UV spectroscopy analyzes the absorption of light in the UV and visible regions, allowing for quantitative and qualitative analysis of organic compounds. The absorption of UV light by organic molecules is largely due to the presence of chromophores, specific functional groups that contain valence electrons with low excitation energy. There are many organic compounds that have conjugated double bond systems in which every other bond is a double bond. These conjugated systems have a large influence on peak wavelengths and absorption intensities. Color in organic compound is associated with the unsaturation. A carbon-carbon double bond in ethane, for example, absorbs energy as electrons in pi bonds are promoted to higher energy levels. Molecules have chemical bonds which are electrons in molecular orbitals. Absorption of light photons causes electronic transitions between HOMO and LUMO. Molecules undergo bond rotations and vibrations. Since different energy sublevels are occupied at room temperature and accessible through absorption, many transitions are possible. UV-vis absorption gives some information on bonding electrons, like functional groups in a compound. If a compound absorbs only UV light and not visible light, it will appear colorless in the cases of many organic compounds. Explanation: UV-vis spectrum. The resulting UV-vis spectrum shows absorption bands corresponding to the wavelength of light absorbed by the molecule. Electronic transitions. UV-vis spectroscopy relies on the absorption of light by molecules, causing electrons to jump from lower to higher energy levels. what we call this is the electronic transitions. UV spectroscopy. This technique measures the absorption of light varying wavelengths through a sample, revealing information about the electronic structure and interaction of molecules. Color and absorption. When white light, which contains all colors, strikes a compound, some wavelengths are absorbed and the remaining wavelengths are transmitted or reflected. The color which we perceive is the result of the wavelengths that are transmitted or reflected. Factors affecting absorption, conjugation, pH, solvent, and temperature can influence absorption spectra. Solvent effects. The solvent can influence the absorption spectrum due to solvent-solute interactions affecting the position and intensity of absorption bands. Chromophores. Specific functional groups called chromophores are responsible for UV-vis absorption. These include pi electrons, which are found in double bonds, triple bonds, and aromatic rings. Absorption of ultraviolet and visible radiation in organic molecules is restricted to certain functional groups known as chromophores that contain valence electrons of low excitation energy. A chromophore is a chemical entity embedded within a molecule that absorbs radiation at the same wavelength in different molecules. Examples of chromophores are dienes, aromatics, polyenes, and conjugated ketones, and so on. Non-bonding N electrons. They are found in atoms with the lone pairs such as oxygen, nitrogen, halogens. Pi and N electrons. Absorption of UV light by organic compounds is mainly due to the excitation of pi electrons with multiple bonds and non-bonding N electrons. Types of transitions. Sigma to sigma star involves sigma electrons and occurs at shorter wavelengths. Pi to pi star involves pi electrons and occurs at longer wavelengths. N to pi star involves non-bonding electrons and also occurs at longer wavelengths. Most absorption spectroscopy of organic molecules is based on transitions of N or pi electrons to the pi star excited state. Antibonding orbital. These transitions fall in an experimentally convenient region of the spectrum 200 to 700 nanometer. Conjugation. The presence of conjugated pi bonds alternating single and double bonds in a molecule is crucial for color. These conjugated systems allow the molecule to absorb light in the visible region, leading to color. The conjugated systems increase the wavelength of light absorbed, shifting absorption towards the visible region. Conjugated bonds in organic molecules absorb short-wave UV radiation around 200 nanometer, but in linear repeats or in ring structures, the absorption shifts to longer wavelengths up to and over 300 nanometer. Isochromes. Groups that do not absorb UV light themselves but can affect the absorption wavelength or intensity of chromophores. Examples. Ethane absorbs UV light with a wavelength around 171 nanometer due to a pi to pi star transition. Buta-1,3-diene. It absorbs UV light with a longer wavelength around 217 nanometer due to the delocalization of pi electrons in the conjugated system. Hexa-1,3,5-triene absorbs UV light with an even longer wavelength around 258 nanometer due to the extended conjugation. Beta-carotene, a pigment in carrots, absorbs blue light in the visible range due to its extended system of conjugated double bonds, resulting in the orange color. Applications. Qualitative analysis, identifying functional groups and structural features. Quantitative analysis, determining concentrations using Here's law. Structural elucidation. Understanding molecular structure from absorption patterns. Detection of impurities. Identifying and quantifying contaminants. How UV spectroscopy works. A sample is exposed to UV with light of varying wavelengths. The sample absorbs light at specific wavelengths depending on its molecular structure. The spectrophotometer measures the amount of light transmitted through the sample at each wavelength. The amount of light transmitted through the sample is measured, and the ab- absorbance or transmittance is plotted against the wavelength. The resulting UV spectrum reveals information about the electronic structure and the presence of chromophores in the molecule. This spectrum can be used to identify the compound, determine its concentration, and analyze its structure. Complementary colors. A molecule that absorbs a particular color will appear as the complementary color on the color wheel. For example, if a molecule absorbs blue light, it will appear orange color. Example, beta-carotene, with its extensive conjugated systems, absorbs blue light and the remaining yellow-orange wavelengths are transmitted, causing us to perceive it as orange. Absorbance spectrum. The UV spectrum shows the absorbance of light at different wavelengths. The wavelength of maximum absorbance, lambda max, is related to the color of the molecule. Terms describing UV absorptions. Chromophores. Functional groups that is responsible for electronic transitions. The group will have characteristics lambda max. Molecular structure or environment can influence lambda max. Axochromes. Substituents with unshared pair of electrons like OH, NH, SH, when attached to pi chromophore, they generally move the absorption max to longer lambda. Bathochromic shift or redshift. A shift of an absorption maximum towards longer wavelength or lower energy. Isochromic shift or blue shift. A shift of an absorption maximum towards shorter wavelength or higher energy. Hyperchromic effect. An effect that results in increased absorption intensity. Hypochromic effect. An effect that results in decreased absorption intensity. N to pi star and pi to pi star transitions. Most absorption bands of organic compounds are due to electronic transitions from fundamental levels to levels N to pi on the excited levels pi star. Absorption bands for these transitions fall in the region 200 nanometer to 700 nanometer. These transitions require the presence in the molecule of an unsaturated group which has pi electrons. N to pi star transitions have low molar absorptivity 10 to 100 liters per mole per centimeter. Pi to pi star transitions have high molar absorptivity 1000 to 10,000 liters per mole per centimeter. The solvent could influence the positions of absorption bands. With increasing polarity, N to pi star transitions are shifted to higher wavelengths, blue shift. Is shifted to higher wave. I repeat, with increasing polarity, N to pi star transitions are shifted to that's a blue shift. So it must be a lower wavelength, 4000 to 7000 angstrom. So lower energy, so lower wavelength. So that's a mistake here. It is not higher. So lower wavelength. This shift is due to unpaired electrons. With increasing polarity, N to pi star transitions are often shifted to higher wavelengths. That's called the redshift. This is caused by attractive polarization forces between the solvent and the absorbent, which determine the decrease of ground and the excited state's energy. This decrease is greater for excited state than for fundamental state, so the difference in energy between the two levels decreases, resulting in a shift of the absorption band to higher wave numbers. That's called redshift. This effect can influence N to pi star transitions, but is covered by the blue shift due to unpaired electrons.